This is Informodel's Level 2 Corrosion Assessment and Clustering Tool. Let's say you're an energy company, you transport natural gas. You want to manage your corrosion integrity threat. You engage with inline inspection vendors, and they have this cool tool called an MFLA tool. It uses magnetism to detect the location and the extent of corrosion. You give these vendors a set of rules. There's a corrosion clustering rule that tells you if different anomalies are interacting with each other. And then there's a corrosion burst model that tells you the pressure at which that anomaly would burst the pipe. So you give them these two inputs, they run their tool, and they essentially tell you what to repair. So you go through the process, it runs across hundreds of kilometers of pipe, it detects a ton of corrosion, and unfortunately, it tells you that there's hundreds of kilometers that need repair. So you excavate those pipes, you spend hundreds of millions of dollars, a lot of time and energy, and with visual examinations, the engineers actually see that, hey, like these, anomalies were not that dangerous, and we just spent so much money on it. This is $1 billion problem. The purpose of the tool is to empower operators to have the flexibility of trying different clustering rules, as well as different corrosion models, and see the impact when it comes to safety decisions, as well as financial decisions. We want to give them a lens that allows them to make the best decision for their company. So now on to corrosion clustering, part 1. So when you look for interaction, there's two dimensions that matter. There's the axial dimension across your pipe, and then there's the circumferential direction. Typically, there's rules like 3 wall thicknesses or 6 wall thicknesses, where if, let's say, you're doing 3 wall thicknesses, you'd see whether the edges of these anomaly at the axial dimensions are within 3 wall thicknesses of each other. Or, and actually, if they're within 3 wall thicknesses of each other circumferentially. So they need to be within that for both dimensions to say it's clustering. And if, let's say, it is clustering, you draw a big box across that area and look at that entire area instead for corrosion. And then you would apply a corrosion model. There's a ton of different models. The big one that we're going to show is called effective area, R-Streng. It's a level 2 assessment that builds a grid across your pipe. We're building 1,000 different grids, and we're doing a factorial experiment to see the worst possible area combination, the one with the weakest burst pressure, and that's the model we provide. Now, a lot of operators might provide a different model, something like a parabolic shape or a hyperbolic shape that would estimate a lot more area loss and lead to a lot more repairs, costing the company millions of dollars more than another more precise model. So let's go through the tool, starting with the template sheet. I'm going to put back that PowerPoint. So let's say you've got your template sheet, and I'm going to show where to get it, and you fill it out. You have different features representing different corrosion anomalies. You got your pipe, you got your inspection name. A big point here is that different inspections will have different clustering. What I meant by that is the current clustering mechanism is only clustering anomalies that are within the same inspection of each other. This is your inspection date. So there's a given date that you ran your tool, and later on I'll show you where the target date is. So you're going to want to grow it to a certain year. Then there's your odometer. Your odometer is your location on a pipe. So if, let's say, you ran it on this pipe, you could say that your initial spot on the tool could be, let's say, 0. And then you run it across your pipe, and it goes up to, let's say, 100. Make it really simple. And it detects corrosion at some location. Let's call it 50. 50 is your odometer. So essentially a spatial location on where it ran. Then you've got your wheel count start and end. Let's say it started at 25 and ended at 75 across this dimension. Now, like obviously these numbers They really mean nothing. It's just for the example. Then you have a wheel count start and end. Now, this actually gives you your angular dimension. So let's say it starts at 12 or 0 o'clock, and it tells you where it's located. So 11 to 1, if I were to draw it, it'd be something like this and that. That would essentially be where your corrosion anomaly is located. Then you got your flaw length. In this case, it would be 75 minus 25, which would be 50. You have your flaw width. Using some math, you can get it based on your angle and your diameter. You've got your flaw depth. So if, let's say, you stop looking at this view and you looked at that view, typically people put peak depth here. So it would be maybe, and this is in inches. So let's say you've got a wall thickness of 0.4 inches, and this is 0.3. That could be a good example. So you're essentially 75% of your pipe wall thickness is gone. Then there's the depth growth rate. So it's just a rate of growth that you're going to use. Length growth rate, width growth rate, distance to the nearest girth weld. This is important because let's say you've got a girth weld here. These girth welds have a heat affected area, and there's a higher likelihood of corrosion. So having this attribute is really useful, especially when it comes to corrosion growth. You've got your wall thickness, outside diameter, your operating pressure. So this is, let's say you've got your pipe. There's a pressure that this corrosion anomaly can resist, and you're operating at a certain pressure. Can your anomaly resist the pressure that you're operating at? Then these are material properties. Let's go over the tool now. So you would go to our website, and then you would simply just download the template sheet. So this is our tool that's available. You download the template sheet. I've already done it. You choose a different model, your R-string level 2. That's the super precise model that we provide. There's different flow stress models. And then you can either use your peak dimensions or your effective dimensions. So if the individual features, you're given something better than a rectangular box, which is not very typical, you can use those better measurements. You've got your axial wall thickness and circumferential wall thickness. This is your clustering rule. So again, axially, if I go here, axially, this is a better diagram. If I look at it in this direction, is this within 6 wall thickness? Is that the rule we want to use between this and that? Perhaps that's a really wide rule and you're going to get big clusters. So you want to say, no, I don't want this rule. I want to use 3 wall thickness. And I didn't show it well here, but it would lead to a lot less clustering, a lot less interaction. Same circumferentially. Maybe you want to change that rule. And instead of using your let's say 6 wall thickness rule here, you're going to want to use something smaller, like a 3 wall thickness rule. And then there's a bunch of shallow anomalies. Let's say this shouldn't be clustering, but because there's a chain of super shallow anomaly that really doesn't pose a threat and could maybe be below a detection threshold, you filter it out. And by filtering it out, you're no longer dealing with this large cluster, but you have a more shallow cluster. I've seen this in industry. And then this is where you choose your corrosion date. What date do you want to do the assessment? Let's say it's December 2023. That's a good date. But if, let's say, you wanted to go further in the future, do the assessment at the end of 2024, you want to project things really far, you can do the assessment then. You got your minimum growth rates. So you run your inline inspection tool, and sometimes it reports no growth, which is it's unconservative, and sometimes maybe it's reporting negative growth, complete garbage. You want to put a minimum growth rate, your depth at the very least. You can also grow length and width. You can see it's much smaller, and oftentimes it's set to 0 here. So you run your tool. I'm just gonna go there. And obviously it's open, so let me go right here. And then you just run the corrosion assessment. Now, running the tool takes a little bit of time. It's not too long. But then you see the results. And this gives you for starting your cluster ID. It's right there. Then you have all the feature IDs that it contained. You've got your pipeline names, your inspection names, your inspection date. You've got your will count start, will count end, all these attributes that I've spoken of. And then you've got, just for starting, your cluster max length, your cluster max depth, your cluster effective length, and effective depth. These are key things. And then you've got your distance to the nearest call logs. And then you've got your failure pressure at the projection year. You see that this is, it would fail at a pressure that's much higher than the operating pressure of 1,000 psi. So this is 1,000. We're projecting that the corrosion anomaly at that year would fail here. There's a ratio called FPR. I won't go into it, but it's essentially telling you that it's posing a moderate integrity threat, but it's not necessarily urgent. Now, I really want to show you this. Let's redo the experiment. Let's change things. Let's use just a different model. So I'm not even playing with the rules. We could do that and get different results, but I'm just going to use a different model. This is going to assume elliptical shape. I'm going to run the tool. You just need to wait for a couple of seconds, and then any minute now you'll see the results. You just press view results. You can essentially see right away there's a big difference. It's now posing a major integrity threat. Just by shifting the model, you go from something that's 1,300 to 1,078. Because you've incorporated so much conservatism, you've essentially said that this is an anomaly that needs to be repaired urgently, spent millions of dollars repairing it, when you could have just used a better model and obtained better quality info. This is just one aspect that you can change. The clustering rules are something that can drastically change results as well. Thank you for listening.